Hello, and welcome to today's review of Chapter 4, Section 3, Prime Factorization and Greatest Common Factor. And before we start with today's review, I'd like to go over a few definitions that we'll be using. Prime number. A prime number is an integer greater than 1 with exactly two positive factors, 1 and the number itself. The numbers 2, 3, 5, 7 are examples of prime numbers. A composite number, on the other hand, a composite number is an integer greater than 1 with more than two positive factors. The numbers 4, 6, 8, and 10 are examples of composite numbers. Note, the number 1 is neither prime or composite number. Prime factorization. Writing a composite number as a product of its prime factors shows the prime factorization of the number. Write the final factors in increasing order from left to right. Use exponents to indicate repeated factors. And then lastly, the greatest common factor, the GCF. Factors that are the same for two or more numbers or expressions are common factors. The greatest of these common factors is called the greatest common factor. You'll use prime factorization to find the greatest common factor of two or more numbers or expressions. If there are no common factors and variable factors, in common, the GCF is 1. To start today's review, we're going to be finding prime factorizations. The diagram to the right shows the only rectangle. There's only one single rectangle that you can make with integer side lengths and an area of 5 square units. So as you can see that the box here, this blue box, the rectangle, has 5 units in it, and it's the unit lengths of this box are rectangle are 1, 2, 3, 4, 5, and 1. So they're all little squares or little rectangles. And there's no way you can move these boxes around to have any other way of getting 5 in a single unit. If you try to cut them in half, you'd have a half a square and a half a square here, and then there's no way you can divide this in any other way. The green objects show how you can form two 4 square figures. Okay, so if I was to say this one over here, which is 4 units, 1, 2, 3, 4, you can see we can have 1 by 4, or we can have 2 by 2. It's still 4 square units. Well, you couldn't do that with the 5 because in order to put these next to it, you'd had to have cut one of them in half. But we have to have whole integer values. So let's start by finding the number of rectangles you can make with each of the numbers of square units that are provided in this list. So for this number 2 here, how many rectangles can we make? So if we look over here, you have 2 and 1 is the only ones you can. There's nothing else other than 2 and 1. So that would be much like the 5, 1 over here. It'd be 2 and 1. There's no any other way of putting that box other than one stacked on top of another. So we're going to find out how many you can make. So in this one, you can only make 1. Okay. For 3, it's the same as 2. You can't get anything other than 3 boxes stacked on top of each other. There's 1 here. For 4, though, like I'm showing here in the green, you can do one set of rectangles here, or one rectangle, and another one here. So it's 2 figures. So here we got a 2. 5 is the one in blue. You can only do 1 set of boxes for 5. For 6, you can do 6 and 1, 2 and 3. So that's the combination. We got 2 here. 7, you can only do 7 and 1. There's no other way you can make a 7 like we did with the 6. So there's only 1 here. For the 8, we have at least 2 boxes we can make. So it's 8 times 1 and 4 times 2. So we're going to say 2 here. And 9, it's 1, 9, 3. So that's going to be, let's say, 2. And then over on 10 here, again, 10 is 1 and 10, 2 and 5. So it's 2. So for which numbers of squares is there only one rectangle possible? Well, We just saw it. It's 2, 3, 5, 7. Any more? Nope, it ends there. So for which numbers of squares are there more than one rectangle? Well, we found that too. It's 4 and 6 and 8 and 9. 9 fits in there, and 10. Okay, so now at the end here it says list the dimensions of the rectangles you can make with each of the following unit numbers and unit squares. So if we had 13, how many, list the dimensions of the rectangles you can make. So that's like saying with the 4, you can do a 1 and 4 and a 2 and 2. So with 13, we can only do what? We can only do, whereas for 13, we can only do a 1 and a 13. For 15, we can do 1 and 15, and we can do 3 and 5. So we're going to skip. That's how many you can do for that one. For 17, all we can do is 1 and 17 because we can't divide 17. For 19, we can do 1 and 19. Okay, 1 and 19. And then for 21, we can do 1 and 21. 1, comma, 21, comma, 3, comma, 7. I didn't list them in order, but it's easier to do them that way. You take them in pairs as you go. So I think that's the what we have here. Did we get them all? 1, 2, 13, 15, 17. Did I miss 17? Oh, no, here's 17, 19, and 21. There they are. Okay, in example 1, under primes or composite, they're asking a question. Is this number a prime number or a composite? Well, we've gone through that a number of times already, but this should be pretty easy. So A says 23. Is 23 a prime or a composite number? Well, as I've already written the answer down here, it's prime. It only has 2 factors, 1 and 23. Nothing else will go into 23 that you can... Like if it was a 21, you could say 3 and 7 would be the another set of factors. But how about 129? Well, it's even. It's not even, so you know 2's don't go into it. Is it composite? Well, if anything else other than 1 and 29 go into it, we know it's composite. So let's try a 3. So 1 times 2, 1 plus 2 is 3, plus 9 is 12. And the 12, I can write it down here, the 12 is, so it's 1 plus 2 plus 9 is equal to 12, and 12 is divisible by 3, so it is composite. There it is here, 1, 3, and the numbers are, if you ran the tree down, you start at the top, 129, and you'd come down and you'd find that there's no 2's, but that it definitely factors a 3. So you take a 3 out here and bring this down, and it's 43 is the other side of this. So you got 129, 3, and you've got a 1 because it's 1 and 29. So those are our factor. We can only do those. 43 isn't divisible by anything, so it's a prime number. So there we have it. And 1 is not a prime number, but it's one of the factors. So we can see that for sure. Okay, in example 1 of check your understanding, they're asking one question. Which numbers from 10 to 20 are prime and which are composite? So let's start off and figure it out right away here. So the prime numbers is 10 prime. Is 10 prime? 10 is even, correct? So it is not. So 10 is not. It's equal to a composite number. How about 11? Is 11 a prime or a composite? Well, you can't divide 11 by anything other than itself in 1, so it is prime. How about 12? Is 12 even? Yes, so it's all automatically a composite number. It's divisible by 3, divisible by 4. It's got a lot of factors, but for primes, we already know that it's not. How about 13? Can you divide 13 by anything other than a 13 and a 1? The answer is no, it's prime. How about 14? Can you divide 14 by anything other than 14? Yes, it's 7 and 2. It's an even number, so it's composite. How about a 15 here? 15 is divisible by 3 and 5, so we know it's composite. How about 16? 16 is even, so it's composite. 17. 17 is not divisible by anything but 17 and 1. It is prime. And 18 is even, so it's composite. 19 is not divisible by anything but 19 and 1, so it is prime. And 20 is even, so it is composite. In example 2, writing the prime factorization. So they use a little nice little thing called a tree, which is it's a factor tree. So what we're going to do is start with the number on the top, and then we're going to divide the factors. You see them there, like the 5s and the 3s and the 11s. It's kind of fun. So we start off with, at the top here, we start with 825. And you can see that it's not even, so 2 doesn't go into it. 3, this is 15. Does 3 go into it? Yes, we could actually have started with a 3. See it? The 3 is a factor. But we ended up choosing to start with the 5 because 5 was a very easy one. We could have started with the 3. We would have had a different set of numbers here, but we're going to go with the 5. 825 is divisible by 5 because it ends in a 5. How sweet is that? 5 is prime, and it's on this side. And if you divide 825 by 5, you get 165. So now the next thing, is 165 divisible by 5? Oops, yes it is. Right there, 5. Bring down a prime 5 over here, and the result is 33. 5 times 33 is 165. Is 33 divisible by anything other than, not a 5? Oh, it's divisible by 3, not a 2, 3. So that is divisible by 3, another prime, and what's left is 11. Oh, and guess what? 11 is also a prime. So the factors, the prime factors of 825 are 5, 5, 3, and an 11. There they are, primes. 3, 5, 5, and 11. So if you're going to write this, they're showing us here that 825 is equal to 3 times 5 squared. We combine the like terms. 3 times 5 squared times 11. And that equals 3 times 5 squared times 11 is 825. And those are your prime factors. They're listed out for you. Okay, in example 2, under check your understanding, we're going to write prime factorizations like we just did in the previous slide for each of these 4. We're going to start off with the number 72. Do the primes for 72. So 72, is it even? Yes. So we know right off the bat that a 2 is a prime. And what is that? What is 70? Half of 72? Half of 72 is 36. So it's 36, it has factors for sure. It's even. So we have another 2, and half of 36 is equal to 18. And 18 is even, so we're going to take another 2 out of there, and we're going to be left with a 9. And as we take, and now there's no more 2's in a 9, but we certainly have 3's, so we can take a 3 out. And when we bring this down, we have a 3 on this side. So we have a 2, a 2, a 2, a 3, and a 3. So what does that come out to? That comes out to 2 cubed, 3 squared. Those are the prime factors in order, the primes. Let's go over here to B, 121. Is 121 divisible by anything, any primes? Well, let's start off with the easy ones. Is there a 2 available? No, it's odd. It's an odd number. Is 3? Can 3 go in there? Is 2 plus 1 is 3, plus 1 is 4. 4 is not divisible evenly by 3. It's not a 4 because it's odd. 5, that doesn't end in a 5 or a 0. A 6, if it was a 6, it would have had to have been divisible by the 2. It's not. Is it a 7? Well, 7 we'd have to decide if 7 goes into 121. And I guess the way I do that is I'd say 7 into 121. And what does that come out to? 7 goes into 12 one time. And 5. 7 goes into 51 how many times? 7 times. Even? No, because there's 2 left over. So 7 doesn't go in. Okay, so this, I'm going to say that this number here is prime. Okay, how about 225? Well, we're going to start. We know right off the bat, you take the easy ones, right? The easy hang, or the low hanging fruit, as we like to say. 225 divided by 5 is what does that come out to? It comes out to, I think, 45, I think is what the number is there. 45. And let's see, 45. 40 times 5 is 200, and 5 times 5 is 25. And so now this is also ending in 5, so it's also divisible by 5. So 45 divisible by 5, we have a 9 times 5 is 45. And 9 is divisible by 3's, and we get 2 3's. So we end up with this one, we end up with 5 squared. I'll go over here, go 3 squared, 5 squared. This one up here was prime. So now the 236. Let's try 236. 236. Is it divisible by 2? Yes. What's half of 236? Well, half of 30 is 15. So it's 115, and 3 is 118. And then we're going to divide the 100. It's even. So we're going to divide that by 2 and 118. So the answer here would be 59. 59. 50 times 2 is 100. 9 times 2 is 18. So 59. What can we divide 59 by? Anything? Well, is it even? No. Is it divisible by 3? 5 plus 9 is 14. No. What else can we do? 5 times, let's see, it's not 5s, it's not 6s. 7, does 7 go into 50? No. So I'm going to say that this is 59 is prime. So there's nothing else you can do here. So it's 2 squared plus 59. Sorry about that little disturbance. I was being interrupted. Okay, so that's it. We have our prime factors taken care of. Okay, and for objective 2, we're going to find the greatest common factor using prime factorization. So there'll be some problems will come up, and we'll find prime factors, and we'll then come up with the greatest common factors of those numbers. Okay, find the greatest common factor of each pair of numbers or expressions listed below. So for A, we have 40 and 60. 40 and 60. What are the prime factors of 40? Well, as we've always done before, we'll start off with the easy fruit. 2. We come up with a 20. 20 is a 2 and a 10. 10 is a 2 and a 5. So that's it. 2, 5 for the 40. 2 and 5. Well, and these other 2. So it's 2 cubed. I'll write it down. It's 2 cubed and 5. So for 60, we're going to do that. We've got a 2. I always like that. 2 and 30. 30 has a 2. 2 and 15. And the 15 has a 3 and a 5. 2, 2, 3, 5. So over here it's 2 squared, 3 times 3 times 5. So what's common? Well, we have 2's common, we have 5 common. There's no common 3, so 3 is gone. The 5, the highest value of 5, and the 2 expressions or 2 numbers is to the first power. So we're going to use 5. And then the highest value we have for the 2's is 2 cubed in one and 2 squared in the other one. So the highest value is the 2 squared. Both of them have a 2 squared in them. One, the 40, has an extra 2 on it, so it has more than just 2 squared. So with it, we're going to only use the 2. So the answer here is going to be 2 squared. And what's the other common one? The 5 is common in both of them, right? So 5. So that 2, and that's 4 times 5 is equal to 20. The greatest common factor, the GCF is equal to 20. Okay, how about this one? A little more complex looking, But actually, it's kind of simpler because you don't have to do anything with the letters. They're already done for you. The only thing we got to worry about is the 6 and the 6a cubed b, and we've got a 4a squared b. Well, for the 6, that breaks into a 2 and a 3, and for the 4, it breaks into a 2 and a 2. So the highest common factor is a singular 2 in each of these. So we're going to write down a single 2. So what's the highest between a cubed and a squared? The a squared is as high as both of them go. One goes higher, a cubed, but they both have a squared in them. So now we have an a squared, and then the highest factor of the b's is there's this singular b in each, so it's b. So this one here is 2 a squared b is the answer to that. 2a squared b. Greatest common factor. And because it has letters in it, we don't know anything further than that. And we see that coming down here. I did the factoring. I put them together. 2a squared b, 2a squared b. Over here, the greatest common factor is 20. So, okay, as the example we just did, let's take and do some prime factorization to find the greatest common factor. So we'll start with the 8 and the 20. The greatest common factor of the 8 is what? What are the factors, of 8? Oh, we have a 2 and a 4 and a 2 and a 2. So there it is, 2 cubed. And for the 20, we have 20, which is 2, 10, 2, 5. It ends right there. It's 2 squared times 5. Okay? So if we're going to write the numbers out, this is an 8, and this is... No, we don't need to do that at this point. Excuse me. We don't need to write the numbers out. We just got to look at a squared is the largest number. So what is the largest number? Is 4. 4 times... Nope, the 5. There's no 5s in this one. It's just 4 is the highest common factor. The greatest common factor. Let's go and look at 12 and 87. So if we start with the 12 over here, we're going to get a 2, and a 6, and a 2, and a 3. And 87. Can we divide 87 by anything? Well, 8 and 7 is 15. And the factors for 3, the divisibility test for 3, is if the digits are added together and they're divisible, that is divisible by 3. The number is divisible by 3. So 87 is divisible by 3. So it's 3. And what is 87? So 87 divided by 3, it's 2. 2 remainder, and we have a 2. 3 into 27 is 9. So 29. And 29 is a prime number. So 3 and 29, and 4 and 3. Well, they both have 3s. And so the greatest common factor is 3. The GCF is 3 for this particular problem. Let's go over here and do 12r cubed. 12r cubed. And remember, we saw that earlier, that the letters are already kind of handled for you already, aren't they? 8r. So 12r cubed goes 2, 6, 2, 3. So we have 2 squared and 3. And over here we have the 8, which is 2, 4, 2, 2, which is 2 cubed. Now what about the r? So we have an r cubed over here, r cubed, and over here we have an r. So the highest common factor here is the r. They both have at least one r in them. And the this one has 3 2s, this one has 2 2s. So it's 2 squared and r. So the greatest common factor, the GCF, is equal to 2 squared r or 4r. Okay? So then let's try this one. Again, 15 breaks down into 3 and 5, and we're done. We have m's 15, m squared n, and 45 breaks down into what? Oh, it breaks into 3 15s, right? So it breaks into a 3 and a 15, and the 15 breaks into a 3 and a 5. So we have, oh, I wrote a 2, 3 and a 5. So if we have 3 squared times 5, and the 45 has an m, so we're going to put an m, and that's equal to 3 squared times 5 is 9 times 5m, or 45m. So what is this one? We have, what's common over here? We have 3 squared, we have a single 3. We have a 5, and we have a single 5. So we have a 3 and a 5 over here. We have 1, 3, and a 5. So this is on this side here is 15. And on this side is 1, 3, and a 5 is 15. We have a highest we've got is an m, a single m. So it's 15m. There's an n here, but there's no n over on this side. So the GCF is 15m. I'll write it 15m. Right there. Okay.